all know, Earth is going through global warming due to human emissions of greenhouse gases. You can see in this video the changing temperatures throughout the years since 1850, which marks the beginning of human influence following the Industrial Revolution. This global warming affects us all, and you can already see its impacts all around us. We see heat waves, droughts, ice melting, effects on storms, fires, and so on. But there is great uncertainty regarding future climate changes, and the scientific community can't give a precise and accurate picture of how our future climate is going to look like. In order to reduce this uncertainty, we must understand the physics of the climate system and the mechanisms underlying future climate changes. So this is our system, the atmosphere. You can see different climate features like precipitation, rain. You can see wind circulation, air ascending, moving horizontally, and then descending, and so on. And the lower boundary of the system is the ocean. And since processes in the ocean affect the surface, we expect that they would have an impact on the changes that we see in the atmosphere. So this is where we come in. We want to understand what is the role of ocean processes in driving future climate changes. How do we do that? We use climate models. These models divide the world into many, many small boxes. And in each box, they solve equations that include all the physics, the chemistry, and the biology that has to do with climate. We have such a model for each part of the climate system. So a model for the atmosphere, the ice, the land, and the ocean. And all these models are coupled together. In my study, we focus on this model, on the ocean model. And what we do is we replace this full physical ocean with a model that includes only the top layer of the ocean called the mixed layer. The temperature changes in this layer can be described by this equation. So you see on the left is the change of temperature in time. And on the right, we have many terms that you can divide into two. Terms that have to do with thermodynamic processes and terms that have to do with dynamic processes. What are each of these processes? So let's look at the illustration. Thermodynamic processes would be the exchange of heat, the heat fluxes between the ocean and the atmosphere. We have sensible heat, latent heat, shortwave and long-wave radiation. The dynamic processes would be the transfer of heat inside the layer. So it could be horizontal transfer, just redistribution of heat. And it could be a vertical transfer, so it's taking heat from the top layer into the deep ocean. And what we do in our study is each time take one of the components of the model of this equation and hold it constant to the values that it had before the Industrial Revolution, meaning before it started being influenced by human. And by holding each time one of the components constant, we can isolate the contribution of this component to the changes that we see. So we can isolate the contribution of thermodynamic processes or the contribution of dynamic processes or the total contribution of their sum of the total ocean processes. I'm going to give you an example for a case in which we used this method to study the role of ocean processes in the changes that we see in the atmosphere. So this case is the projected net precipitation increase in the northern hemisphere winter. What is net precipitation? We define it as the difference between precipitation and evaporation. You can see here in the color bar that we have here the change in the temperature by the end of this century. So positive values, the green colors, would be a net precipitation increase, meaning that it would get wetter. And the negative values, the brown colors, is a net precipitation decrease, meaning that it would get drier. Here you can see the results from a full model, a regular model before we changed it. And it's a map. So we have on the x-axis the longitude and the y-axis is the latitude. And you can see here on the left it's Europe and Asia, and on the right it's America and Greenland. I hope you have the orientation. And you can see that there is a general increase in net precipitation throughout the whole region. Now, this increase is not only projected to happen in the future, it's also been observed in past decades and been widely studied. And previous studies have argued that the surface plays an important role in driving the changes that we see. But no one before has fully quantified the role of the ocean in driving those changes. So that is what we're going to do, and we use our method, as I explained before, to isolate the contribution of the ocean. So on the right, you have the contribution of only ocean processes to the net precipitation increase, while on the left, you have the contribution of all processes in the climate system, the atmosphere, the land, the ocean, and so on, to the changes. And you can see that the pictures are almost identical. They're similar both in magnitude and in pattern, which means that the ocean is responsible for the changes that we see in the full model. So we asked before, what is the role of ocean processes in future climate changes? We have the answer. In this case, it's a significant role. It drives the changes that we see. Now we can further decompose the total contribution of ocean processes to the contribution from dynamic and thermodynamic processes. And this is what we get. So let's walk through this region by region, starting from the land. You can see over the land that for thermodynamic processes on the bottom left, we have high positive values, while for dynamic processes on the bottom right, we have negative values. This means that thermodynamic processes act to increase net precipitation, while dynamic processes act to reduce them. And in these opposing effects, eventually, thermodynamic processes win, and we get a total of an increase for the ocean. I remind you, it's on the top right. Okay, for the Pacific case, we get a very similar picture. The increase in net precipitation due to the ocean is caused by thermodynamic processes, while dynamic processes act to reduce them. But for the Atlantic, we get an opposite picture. We get that the dynamic processes act to increase net precipitation, while the thermodynamic processes do the opposite and try to reduce them. So what we did in our study is take each of these regions and try to understand through which mechanism do each of these ocean processes act in order to change net precipitation. I'm going to give you an example for the mechanism that we revealed for the land case. So we want to understand what is the mechanism through which thermodynamic processes act to increase net precipitation, and what is the mechanism through which dynamic processes act to reduce them. Starting from the thermodynamic case. We have our sun, and the sun radiates, and this radiation arrives at Earth and is absorbed in the ocean. Then thermodynamic processes, which I remind you are these heat fluxes between the ocean and the atmosphere, emit the heat back. And by that, they act to warm the surface. And of course, if we have global warming, they would act to warm the surface even more. So we have warming of the surface. Therefore, we would get more evaporation, more available moisture. And in fact, in regions of higher temperatures, we get more evaporation than in regions of lower temperatures for the same amount of warming. So in lower latitudes, where it's warm, we would get more increase in evaporation than in higher latitudes, where it's cold, near the pole, where we would get a lesser decrease. So the gradient between the south and the north would increase. So we have a total of a moisture gradient increase. Now, the turbulent flow has a very important role in transporting moisture in the atmosphere from places of higher concentration to places of lower concentration. So if we have an increase in the moisture gradient, the turbulent flow will transport more moisture down this gradient. Eventually, we would get a convergence of it and a net precipitation increase. So we have here the mechanism through which thermodynamic processes act in order to increase net precipitation. what happens for the dynamic case? So I remind you that dynamic ocean processes take heat from the top layer of the ocean into the deep ocean. And by doing that, they act to cool the surface. If we cool the surface, we have less available moisture, less evaporation. We would get a decrease in the moisture gradient from south to north. Then the turbulent flow would transport less moisture down this gradient. We would get less of a convergence and eventually a net precipitation decrease. So this is the mechanism through which dynamic processes act to decrease net precipitation, and we see that it's exactly the opposite mechanism as we saw for the thermodynamic case. So I want to conclude. We saw that the ocean plays a key role. It drives the net precipitation increase that we see over the northern hemisphere winter. We saw that thermodynamic and dynamic ocean processes have opposing effects in driving this increase and also have opposite mechanisms through which they do these changes. And since we see that the ocean plays such an important role in driving this specific climate change, it highlights the importance of better investigating and monitoring ocean processes in order to reduce climate uncertainty and improve our preparedness for future climate changes. Thank you.